Welcome to this lecture on modal analysis of vibrations. So we will first look at a simple example of 2 degrees of freedom system that we have been talking about in the previous lectures, and develop this process of trying to understand how to describe vibrations using modes. This analysis actually is very general and can be extended in a very natural way to multi-degrees of freedom systems. But we will concentrate on just a 2 degrees of freedom system and derive all the concepts in all generality, but using this example. So we saw that this system, this 2 degrees of freedom system, can be written down in this following form. If you consider small vibrations of these masses and you write down Newton's equations, you end up with a second order matrix differential equation. So since this is a 2 degrees of freedom system, M will be a 2 by 2 matrix, C will be a 2 by 2 matrix, K will be a 2 by 2 matrix, and X will be a 2 by 1 matrix with elements X1 and X2 as its first and second elements. And F is the 2 by 1 matrix where F1 will be this force and F2 will be 0, since there is no force acting on this. So if you notice, so this is a matrix differential equation. So if you have many degrees of freedom, well, you will have a similar equation, but these dimensions will change appropriately. What we are typically interested in is in systems where you have very light damping and system is operating near resonance conditions. Or when will it operate near resonance conditions? That is in the case where the damping is very low. In this case, well, these equations reduce to the following form, where omega is m, so you multiply both sides by m inverse, and then with c is almost equal to 0, this equals that, where omega is given by m inverse k, and if you write it down explicitly, well, these elements of m inverse k or the omega matrix is given by this in these notations, where these are given by this in terms of the system parameters. Now recall that we saw that in a previous lecture that the resonance frequencies for this 2 degrees of freedom system was given simply by the determinant of this matrix. So in other words, the characteristic polynomial with S replaced by I omega. And again, omega is this matrix over here. And so if you explicitly write it down, it is something like this. And then if you write it further, reduce it, it is something like that. So the values of omega for which this is 0 are gives you the resonance frequencies of your system. So in particular, we find that this will be a fourth order polynomial in omega or a second order polynomial in omega squared. So the omega 1 squared and omega 2 squared will be the eigenvalues of this matrix. So this, if you notice here, this is an eigenvalue problem. So if you equate this to 0, that is an eigenvalue problem. So these omegas are the eigenvalues of this. And so the resonance frequencies are given by the eigenvalues of the omega matrix. So the eigenvalues gives you the resonance frequencies. Now we know that every eigenvalue has a corresponding eigenvector. So why do the eigenvectors tell us? So let's take a look at that carefully. So let the eigenvectors be x1 bar and x2 bar corresponding to the eigenvalues of omega 1 and omega 2. So what does that mean? That means that x1 bar satisfies this, where, well, omega, so xj bar satisfies this, where j is 1 or 2 depending on the eigenvalues 1 or 2. And so what are the values of xj bar that satisfy this expression over here? And they are called the eigenvectors. So if you find this eigenvector, since it's a 2 by 2 matrix, it has 2 eigenvalues, it has 2 eigenvectors. And we know that if the eigenvalues are distinct, and it's in typical vibration problems, they are distinct, and therefore the eigenvectors, corresponding eigenvectors, we know are orthogonal to each other. So if you put the eigenvectors in columns and form a new matrix called T, we easily see that omega times T. So if you multiply omega times T, it should be equal to what? Omega times xj is this. Therefore, omega times t is something like td, where d is this. That follows from this. So this expression is what we have written down over here in a compact way. So t is x1 bar, x2 bar as columns, and omega x1 bar is omega squared, omega 1 squared x1 bar. So that's what we have written down over here. So we notice that this relationship holds. And now let's define a new set of variables instead of x. So x are the physical variables or the physical masses, but we will define a new variable using this matrix over here. So we will define z to be in the following form, or in other words, z is equal to t inverse x. And z will also have now z1 and z2, two components. And if you write down using z, the differential equation, the original differential equation of a system in terms of z, we get this. And now this, if you notice, is a very simple form. Why? Because if you notice that this is a 4 by 1 matrix in this case, and if you define these quantities, then this expression reduces to this set of uncoupled second order differential equations. So, or each of these z1 and z2 are simple spring mass systems. So what have we done over here? We have used the eigenvectors of the omega matrix and found a new coordinate system in which the original differential equation is equivalent to two uncoupled spring mass systems or uncoupled oscillators. So in terms of the original coordinates, since the original coordinates are equal to t is z, we find that the original coordinates, if you expand this matrix multiplication, is given by that. Since t has columns t x1 bar and x2 bar, z1 is z1 z2, you multiply that, you get this. So this is nothing but an expansion of this. So what does this tell us? This tells us your actual solution or the actual response of your system is a linear combination of these two solutions of these two differential equations. And that is very interesting. And it also shows something very interesting. So in the original system, the external force was only acting on the first mass. But now we see that through this coupling that comes through this T, we say that the force is actually coupled to both these oscillators. So in the first case, the force was only not in the first case, in the original coordinates, the force was only associated with one of the coordinates. But now in this new coordinate system, that they are uncoupled, but the force is now appearing in both of the systems, and it's the same force that you see over here. So again, so to summarize, we saw that our original differential equation reduces to a couple of uncoupled second order differential equations or second order oscillators or second order spring mass system. So if you had a multi-degree of freedom system, this analysis will be exactly the same, since we know that we see that this is very general expression. So then depending on the dimension of this, you will have many of these z's. So if you had an n degree of freedom system, you will have n second order differential equations, uncoupled differential equations, where the force appears in all of them. And so since x is given by that, where x1 bar has two elements, the eigenvectors have two elements. Now if you define this new variable of this divided by that, so R1 is, so J is, so for the corresponding 1 is the first eigenvector. When J is equal to 2, you get the second eigenvector. So for the first eigenvector, if you divide by this, that ratio is R1. For the second eigenvector, if you divide this by that, that is this ratio R2. Now if you rewrite this, so if you pull x1 1 bar out of this expression, and then it will be R1, and in the second one, if you put x1 bar 2 out of the expression, then this will be R2. So if you write it down, so if you use this notation and write this thing down, you get this. So this actually tells you something very interesting. If you carefully look at this, this tells you something interesting. So again, let me summarize. So we had our original system described by this coupled set of differential equations where the force was only acting on one of the masses. So the force was not acting on this one. But we found a new coordinate system using the eigenvectors of the omega matrix. And in this new coordinate system, this set of coupled differential equations become a set of uncoupled second order differential equations, or a set of uncoupled oscillators. But the force will be appearing in all of the oscillators. Now we use the eigenvectors and we normalize them. And using that normalization, since x is given by t times z, which is this expression over here, we find that the actual solution is a linear combination of these two solutions. So we have two second order differential equations. You have the solution of those two second order differential equations. This says that your actual solution is a linear combination of these two solutions. And so let's look at two cases. First, we will look at the case where there is no forcing, free vibrations, and then where is forcing, but that forcing is sinusoidal. So let's first look at the free vibrations case. So there's no force, force is zero. So then this reduces to that set of equations, but still the solution is a linear combination of these two, as we saw before. And so if you look at this, this is just a spring mass system. The solution of this we have seen takes this form. This is again another spring mass system, and the solution takes this form. Therefore, the solution of this original system is just a linear combination of this and that with these amplitude ratios. And so it is interesting to note that if you had this initial condition where the initial velocities of both these were zero, and the initial displacement of this and this were exactly like R1, 1. So they corresponded to this column matrix. So you displace this by 1 and this by, this by 1 and this by R1, then that is this initial condition. Then we see that the solution is simply that, because this term will vanish. And on the other hand, if you had an initial condition that was equal to this, then the solution is that. Whereas, because this part will be zero, these terms will be zero or very close to zero. So what does this tell you? This tells you that if you start your system in a configuration that is close to this, you will see only this part of the solution. If you start your system in a configuration that is close to this, then you will only see that part of the system, the solution. So these are basically called the modes of vibration. So let me summarize that. So if I had initial condition, so in this particular example, if you look at this particular example, we can explicitly write it down. We can find that if under these initial conditions, the solution is this, and this is what actually you see. So we will find, if you look at those expressions that we derived a couple of slides ago, R1 is positive, and therefore, if the mass 2 moves by 1 unit, R1 will also be positive, but some magnified by some scalar. If these two masses are the same, and then R1 will be also very close to 1. And so you see that both of them are moving in phase with each other. On the other hand, if you had initial condition that was close to R21, and R2 you can show is actually negative in this case. And so what does that tell you? So if the second mass moves 1 unit, the first mass will move minus R times 1 unit, and that is what you see over here. So these are two actual simulations of this differential equation for these two initial conditions. So what does this tell you? This tells you that the system has two distinct ways of behavior, modes, and a general solution is a linear combination of these two distinct ways of motion, or these two modes. And now let's look at the case where there is some forcing, and the forcing is sinusoidal. Now again easy. Why? because now these are two uncoupled differential equations and they are simply two spring mass systems. And we have seen that, well, if this was sinusoidal or if this was sinusoidal, then Z1 is given by something like this. Z2, the solution of this differential equation, is given by something like this, where the amplitude is magnified by a frequency dependent function and the phase is shifted by a frequency dependent function. So we saw this very early in these lectures, and we have derived these things. And where the amplitude magnification is simply the magnitude of the transfer function. In this case, it happens to be that. And the phase shift is given by the angle of that transfer function. So that is what you see over here. And we notice that the amplitude magnification becomes very large when omega is close to omega j. So that's the resonance condition. So Z1 will be very large when omega is close to omega 1, and Z2 will be very large when omega is equal to close to omega 2. So when omega is equal to close to omega 2, Z1 will be small, but Z2 will be very large. When omega is close to omega 1, Z1 will be very large and Z2 will be very small. And therefore, so since the solution, general solution is a linear combination of these, what you will notice is that this system of this 2 degrees of freedom system of two masses will be behaving as a linear combination of this and that. Or in other words, it will also have both will be oscillating at the same frequency of omega, but as some linear combination of this. So I have given you a couple of assignments for you to try it out for different systems and derive these things, and hopefully that will provide you a better understanding of what I have been talking about so far. So again, so if I just write it down explicitly, so to summarize, we have this differential equation. You use the eigenvectors of this matrix to find a new set of coordinates, where this differential equation reduces to the form of two uncoupled differential equations. The solutions of these two uncoupled differential equations take this form. Solution of this is something like that. Solution of this is something like that, where these amplitude magnifications are given by this over here, and the phase shifts are given by this over here. The general solution we saw is x is equal to tc, therefore a linear combination of this solution plus that solution. And so if you write it down explicitly, what you get is this. So now let's ask this following question. What happens if omega is very close to omega 1? If omega is very close to omega 1, this term, the magnitude, will be very large, but G2, this 2 will be small compared to that. Now, if omega is close to omega 2, this will be very small compared to this. And therefore, we make the following observation. If omega is very close to omega 1, what you will see is this term being very large compared to that. Why? Because this is very large compared to that term. And therefore, your solution will almost look like this. On the other hand, if omega is equal to omega 2, very close to omega 2, this term will be very large compared to that. And therefore, what you will be mostly seeing is this part, and whereas the contribution from this is very small. So you will see that when omega is close to omega 1, you will get a mode 1 behavior. And when you have omega is equal to omega 2, you will have behavior that is very close to the mode